In this presentation, we will be covering hybrid SPECT-CT technology. This presentation is supported by the International Atomic Energy Agency Technical Cooperation Project POL9027, which is entitled Enhancing the Capabilities of Positron Emission Tomography Departments to Provide High-Quality Imaging and Therapies to Promote Safety Culture. These are the learning objectives for the presentation. We will cover equipment, both traditional scintillation detector devices and those systems made with CZT detectors. We will talk about image formation and corrections, calibration, quantitative SPECT outputs, challenges, and harmonization. So let's start by exploring the technology associated with the traditional scintillation detector SPECT-CT system. The traditional scintillation SPECT detector, which I've highlighted in the image and the schematic at the top of this slide, can be described as having four components. The collimator, which provides positional information. Only ionizing radiation parallel to the collimator holes are allowed through to the scintillation crystal. Then we have the scintillation crystal, which takes these ionizing radiation photons and creates light photons. The next stage is the photomultiplier tube array, where light photons are converted into electrons and then significantly amplified in their number. And the final element are the processing electronics, where positional and energy information is gathered and the image is digitized, ready for display. This detector technology has served us well for many years and still works well for us. But standard scintillation detector systems do have some disadvantages. They're really bulky. The photomultiplier tubes are several centimeters, the crystal's thick, and the collimator itself obviously adds to that, but the main detector system itself is really quite bulky. And actually, relatively speaking, the energy resolution of these scintillation devices is quite poor at around 10% full width half maximum. While semiconductor detectors are compact, which provides opportunities for really innovative scanner design. And they also have really very good energy resolution, around 5% now full width half maximum for technetium-99m. Examples of semiconductor detectors are lithium drifted silicon, high purity germanium, cadmium telluride, and cadmium zinc telluride, or CZT, which is the one that we see most on the market. So how do these semiconductor detectors work? Gamma or X photon hits the depletion layer of the semiconductor, where an ionization causes negatively charged electrons and positively charged holes to be created. With an electric field across the semiconductor, the electrons go to the positively charged anode, and the holes go to the negatively charged cathode to create a signal. This signal can then be processed and counted. A clear advantage here is that the radiation photon is measured directly as an electrical signal, unlike in a scintillation detector, where we go through several stages from the incident radiation photon to the electrical signal. To go from a detector to a scanner, the whole field of view of the system is made up of 2 to 3 millimeter detector elements to create a pixelated detector. And often we have one-to-one collimation, so that the photons pass through the collimator to directly hit the detector below, as we are showing in the figure on the left. Because of the cost of these detectors, initial scanners were organ-specific. For example, for the heart, where we had the Spectrum Dynamics SPECT and the GE530C scanners. As production of the detectors has improved, whole body systems are now available either with a traditional camera design, such as the Discovery 870 CZT system from GE, or the Spectrum Dynamics Veriton or GE Star Guide, which take an alternative approach of having a ring detector with multiple fingers of these detector elements. And here we see three of these scanners. The cardiac specific DSPECT on the left here, so we can see the detector elements. They're quite relatively small detectors because they only need to focus on the heart. In the middle here we see the GE Discovery 870 CZT. You can see each of the detector modules sitting in a traditional detector design. It's the standard 50 by 40 centimeter design with a collimator sitting above that. And on the right, we see these finger detector CZT systems. Here it's the Veriton system from Spectrum Dynamics. The GE system is similar. But you can see we have these fingers, and at the end of each of these fingers, there's an array of CZT detectors for us to capture the imaging information. And of course, we add our SPECT system back to back with a CT to produce a SPECT CT system. Because the system is set up with a known translation between the CT and the SPECT, we can then run various protocols to acquire a co-registered SPECT and CT. There are a number of ways we can acquire the data. We can localize with a CT and then perform a SPECT and a CT based on the localizer. We can localize on emission data before acquiring the SPECT and CT, or we can do the SPECT, a SCOUT, and a CT. And the CT comes with various specifications. Some systems come with a low performance CT, a low slice CT, which is really designed primarily for attenuation correction. Many systems have a slightly higher performance than that, with more than 8 slicer CT configuration to perform attenuation correction plus localization. And some of the top range SPECT CTs also allow you to perform standalone radiology quality CTs. It's really important before you buy one of these systems to know what you want from the CT before buying. It's quite easy to buy a very high specification CT to do nothing more than localization and attenuation correction, which isn't really appropriate. We will now discuss the image formation and reconstruction on our SPECT CT systems. So how do we get our 3D images? How do we move from projections to a 3D reconstructed image? Well, there's been two ways that we've traditionally done this. The first is filtered back projection, which is now rarely used. Most systems now use reconstruction that is iterative. The base of iterative reconstruction is a method called maximum likelihood expectation maximization, or MLEM. But more common are the things based on this, which is the ordered subset MLEM, otherwise known as OSEM, or ordered subset conjugate gradient. So let's look at how these iterative reconstruction methods work. And I want to acknowledge Brian Hutton, my old professor who lent me this slide. So we have our patient, which we see on the left here. Let me put my pointer on again. So here's our patient. And from the patient, we'll get a number of projections. So what do we do in iterative reconstruction? Well, first of all, we make an estimate. So we'll estimate the image that we think we've got in the scanner. And what we do there is then we'll not back project, but forward project to work out the projections we think would come from our estimated image. And then what we can do is we can compare these estimated projections to what the scanner actually gave us and back project it and update as original over estimate. So we'll update and then get a new estimate of our image. So you can see what we've got here. So now this is our new estimate image, which we've updated based on this original over estimate ratio. And we go through this again. So we'll now forward project this estimated image. We get some estimated projections and we go through the cycle again. We compare this, we update original over estimate to get our newest estimate image. And we go through this until we get to a point where we are happy that the image is either exactly the same or close enough for what we need it to do. Of course, we rarely use MLEM reconstruction and instead use OSEM or ordered subset MLEM instead. This is because maximum likelihood expectation maximization is computationally really expensive, because what we're doing at each iteration is comparing all the projections from our estimate to all the projections in the acquired data. And that takes a lot of computational energy. So instead, we use this ordered subset MLEM technique. And what we do here is that we group projection data into ordered sequences of subsets. So for example, if we choose a subset size of 4, we'll do this sub-iteration, just comparing projections 1, 17, 33, 49. And then we'll work through each subset. So we take the next bunch of subsets, etc., until we get the full iteration. So then we repeat that for the next iteration and go on like this. And what that actually gives us is it gives us an order of magnitude saving in reconstruction time. One thing I want to mention here is, how do we compare this? Well, in ordered subset MLEM or OSEM, we define it by the number of subsets and the number of iterations. So, for example, if we said we had 2 iterations and 20 subsets, if we had a SPECT acquisition with 120 projections, would mean each subset size is 6. Now, for 2 iterations and 20 subsets, if we multiply that together, it tells us that this is effectively equivalent to 40 iterations of the full MLEM reconstruction. To get high quality quantitative SPECT imaging, we need to apply corrections. So we need to apply corrections for degrading effects such as attenuation, scatter, resolution losses, and dead time effects. And we also need to apply a calibration to convert what in SPECT is our native acquisition in terms of counts, to convert those counts into activity concentration. Almost always, attenuation correction of SPECT is performed using CT scans. That is because CT scans measure attenuation. The Hounsfield unit is a measure of attenuation. And if you make any measurements on CT scans, you'll know that what you're measuring is Hounsfield units attenuation. So how do we get our attenuation correction for SPECT? Well, we know that there's a bilinear relationship between the attenuation at CT energies and SPECT energies. So I'm showing an example on the right here. So you can see it's bilinear in that it has one slope up to a point, and then it follows a second slope. You'll also notice here that with different CT energies, the relationship changes. So we need to have different relationships and conversions for different CT energies. And similarly, if we had an image up here for an iodine-131 spectrum conversion, which is a lot higher energy, you would see a different conversion relationship again. So these bilinear relationships, we have a library of them for different CT energies, but also for different SPECT emission energies. So using these bilinear relationships, we can convert from CT attenuation in Hounsfield unit to SPECT attenuation. One thing to mention is that these relationships fail with a contrast. So if you have IV contrast, less so oral contrast, but if you have IV contrast in the CT, it will affect your conversion values. It falls out of this bilinear relationship. Most manufacturers, though, do have a system where you can correct or deal with these accumulation of contrast and make the appropriate attenuation correction. But these tend to be, they need to be selected manually. And what then happens is that the attenuation information from the CT translated into SPECT energies is then incorporated into the iterative reconstruction. And what about scatter correction? Well, scatter correction can be performed in one of three ways. The first is, probably the most common, is to use this dual or triple energy window scatter correction approach. So what we have is we have our normal energy window that we would have over the photo peak, for example, at 140 kV for technetium. And we also add a separate scatter window. So in this image on the right, this is our photo peak window. We'll add a scatter window below. And sometimes if we have higher energy peak photo peaks as well that are going to be scattering into our photo peak, we'll also put an energy window above this main photo peak energy as well. So using the number of counts we get in these scatter windows, we can subtract or make an estimate of the amount of scatter that comes into the photo peak. We'll subtract those counts before reconstructing. A second method is to use effective source scatter estimation. I won't go into it in too much detail here. I think it's beyond really what we're trying to cover here, but I do give a reference. And the third method, which is available on Hermes at the moment, is to use Monte Carlo-based scatter correction. And again, I won't go into details, but there's a reference there if you want to know how that works. Resolution modelling helps improve the spatial resolution of our SPECT images, and through its algorithm can reduce noise in the image too. But how does it work? Well, we know in SPECT that spatial resolution worsens with increasing distance between the source and the detector, as we're showing in the image on the right there. So if we know the distance between the source and the detector, we know the resolution effect, and we can put this factor into our iterative reconstruction. There's two forms that we can use of resolution modelling. The easiest is to just consider the geometric effects of the collimator hole, or if we want to take a more complicated approach, we can also consider septal penetration effects. That's where the photons actually go through the septa and still get through to the scintillation crystal and affect the spatial resolution. Dead time is something else that can be important in quantitative SPECT, although it is mostly applicable to post-radioligand therapy imaging where high levels of activity can give really high count rates. And as we can see on the image on the left here, if ideally as we increase the flux of radiation hitting the detector, we get a linear response of what's measured on the scanner. But actually what happens in reality is that we get this loss of counts, which at very high energy, takes this downward trend as well. So what happens with these count losses? It can affect the measured energy that we get in the scintillation scanner, which then also can affect the measured position too. Now, of course, the position is important. If it's putting the photon in the wrong place, then that's going to affect image quality. But getting the wrong energy too can also give us degradation of our imaging, because, of course, we have energy windows. And if those photons then fall out of our energy window, it's going to affect our image quality. Systems tend to have high count rate modes available to them, but sometimes these can be challenging if you're using multiple energy windows, for example, for scatter correction. The final point of consideration in our quantitative SPECT is the calibration to convert the counts that we get natively in our scanner to activity. We can calibrate the SPECT scanner in one of three ways. So one way is to use a distributed planar source. So this method uses a Petri dish containing a known activity of a known amount of activity. This is the method used by GE. It's going to assume that all counts that are acquired in a planar acquisition are going to be taken into the reconstruction. Like PET, the second method is to use a cylinder. So we say in PET, we traditionally calibrate our scanner using a cylinder of known activity. We can use that method in SPECT as well. So, of course, we need to know the volume of the liquid in the cylinder and the activity, so we get an accurate activity concentration. This method is used by Hermes and MIM and Siemens Broadquant. It does get affected a little bit by the reconstruction you use, so you just have to be aware of that. The third method is the use of NIST point sources. So this is actually only specifically for Siemens scanners at the moment. So what this method uses, NIST is a metrology lab, a primary standard. So it can produce sources or can tell you with great accuracy the activity in your sources. So they transport and provide you these sources that are analogues of the imaged radionuclides. So it won't be technetium, it'll be cobalt because it's longer lived, and the same for other energies as well. And the advantage of this method is that you then know you're calibrating your scanner to an activity that is traceable to a primary standard, to a metrology lab, which means that you take any issues with the accuracy of your radionuclide calibrator out of, it becomes a non-issue. The radionuclide calibrator is very important in the quantitative imaging chain. The accuracy of your SPECT calibration is going to be dependent on the accuracy of the activity measurement in your radionuclide calibrator. This is assuming you're not using those NIST sources. And dosimetry is an application of quantitative SPECT, and we know that the organ and tumour dose is going to be directly related to the activity that you measure on your SPECT scanner. So the accuracy of the calibrator, therefore, is really important in quantitative SPECT, as I said, except SPECT, where they use these NIST sources. In PET, if the same calibrator is used for calibration and for the patient, any measurement bias cancels out, assuming you're doing things like SUV. Accuracy is less important in PET, but in SPECT, it becomes more important because of this direct relationship between activity and dose when we're doing dosimetry applications. So what are our quantitative SPECT outputs? Our direct output from a calibrated scanner is activity concentration, which really is mostly used in dosimetry and is really only helpful in dosimetry. How it's used is I'll show you in this image here. If we look on the left-hand side, we have these images at various time points after we've given our radioligand therapy. And on the image on the right, what we can do is we can see the activity concentration at various time points following the therapy. And you recall that to understand the dose given to a tumour or to an organ, we need to integrate under this curve. So the advantage of quantitative SPECT here is that our region or volume of interest measurements are measured directly in terms of activity. More derived and often more useful metrics are normalized uptake measures such as SUV or standardized uptake values, which normalizes the activity concentration in the area of interest to the injected activity and the body habitus of the patient to give a more independent measure of uptake. This is starting to gain traction in SPECT in both benign and metastatic bone imaging and in the assessment of disease progression. Another metric that we're seeing is an assessment of disease burden. So what happens here is we sum up the volumes that are defined in the image that are above an SUV threshold. So we set the threshold to define the level at which we consider the feature to be diseased. Of course, we have to then remove physiological uptake volumes from there to make sure that these volumes only consider the disease. But if we then sum up all these feature volumes, we get an overall estimate of the disease burden in the patient. Finally, another measure that we use is the percentage of injected dose per gram of tissue. And this is mostly used in dosimetry applications. I want to give an example how quantitative SPECT can be used to determine disease progression. And I'm referring to a paper from Meyer et al. In 2023. So what they did is they performed imaging following various treatment cycles of their radioligand therapy. And using these images, they used software to segment lesions according to a predefined SUV threshold. And by summing up these resulting volumes, they were able to determine the disease burden at each cycle. And of course, they could then follow these sequentially through each cycle. And if we look at the image on the right here, we can see a responder. So this is the baseline PET, but they had a SPECT after the first phase of imaging, first cycle of therapy, and a SPECT after the second cycle of therapy. And you can see they've got the total tumour volume here, which is clearly reduced both visually and numerically between the two cycles. They have another case where they show disease progression. Again, you can see how the total tumour volume has changed visually and numerically. And another example of mixed response. So I think this is quite a nice example of showing disease progression using quantitative SPECT. So let's now talk about the challenges around quantification in SPECT CT. We know that the spatial resolution of SPECT is quite poor. around 1 centimeter. And this will affect what we see and what we measure in our image. So this is a nice cartoon from Soret many years ago now. So what we're seeing on the left is our pointer. We're getting our true image, but by the time it's gone through our system with a limited spatial resolution, we get a spreading out, a spilling out of activity, and also a reduction in the intensity of uptake as well. And we can show this in this series of figures here. So I've got I've pixelated a feature here, but because of the limited spatial resolution, you can see that we get reduced uptake, but you also see that the extent of the uptake grows. It spills out from the original volume. And similarly, if we have a smaller object here, we can see a reduction in the maximum counts, but also a spill out of counts to make the volume look bigger. Conversely, I know it's quite rare these days, but if we were looking at a cold feature, you can see the spill in of neighbouring counts into this cold feature. So, the size of the cold feature seems smaller. So I think I mentioned this in the introductory talk. This is the effects we get of this partial volume. So any structure with a diameter of less than 2.5 times the spatial resolution will be affected by partial volume and will give us a reduced signal. And the recovery coefficient is depending on the object shape and contrast. So we have this phantom here, and we can show that our recovery, reduces. The measurement of uptake we get from the scanner is going to be reduced as the size of our features reduces. Another partial volume effect that is often considered in MRI, but rarely thought about in SPECT and PET, is if our voxel either partially contains two homogeneous tissues or contains heterogeneous tissue. So let me just try and explain this. So here's our feature. And in this voxel here, we see that we have a reduced uptake. And why is it reduced? So let's zoom in to see what the constituent components are of this voxel. And what we actually see is that we have two tissue types, this dark tissue type and the lighter tissue type. So of course, when we look at how that would be represented in the voxel, we get the average of the tissues or the uptake in these tissues that gets transferred into the final image, and that's why we get this averaged value. Alternatively, if we look at this example, again, we're getting some kind of average, and if we zoom in to see what the constituent parts are of this voxel, is we see we've got heterogeneous tissue. So even though it seems to be some kind of average, when we zoom in, we can see actually it's still the two levels of uptake, but just quite heterogeneously distributed. But in the final image, it's going to be represented by this average. So this is the second type of partial volume effect. So how do we correct for these partial volume effects? Well, to account for the mixed tissue example I've just shown you, we can use, for example, an MRI to know where the tissue is and try and associate the uptake appropriately. Or we can just use information about the spatial resolution of the system to deconvolve the image to show what the uptake should be. So in the example here, you can see we've used an MRI and segmentation to try and associate the counts to where the tissue actually is in reality. Another way to correct for partial volume is to look at the known losses of signal from a NEMA image quality fandom to work out what the signal should be. So, we have this small feature. We know this small feature is only going to give us a recovery of 75%. So we can then we can increase the value that we measure to, give it the true value that we're looking for. But as we've mentioned before, these curves are contrast dependent and position dependent in SPECT as well, which is an extra challenge. And we assume that the area of interest in the clinical image is a sphere, which is not always the case. But there are other methods coming to help us better correct for partial volume effects in SPECT. Another challenge for us in quantitative SPECT is the lack of sensitivity. So we know that in some applications, mostly in oncology, ideally in SPECT, like in PET, we want to image from the eyes to the thighs, or maybe even to do a complete head-to-toe scan. But in SPECT, one bed position covers 40 centimeters. So we're going to need to do multiple bed positions to get those eyes to thighs images or to do a total body scan. The challenge comes in that in SPECT we have this collimator which massively restricts the sensitivity of our scanner compared to PET. And each SPECT, depending on the radionuclide and the radiopharmaceutical, it could take anywhere between 15 and 40 minutes. So let's assume it was the worst case scenario, 40 minutes. If we have to do 2 or 3 bed positions at 40 minutes per bed position, you can see the scan is just really far too long for the patient. So, the scanning durations really can be quite difficult for the patient and also for the clinic when you're trying to book so many patients in. What makes life worse, of course, is if we're doing dosimetry, where we're wanting to look at uptake at multiple time points. Not only have we got one of these very long scans, we're going to have several of them. So what solutions have we got in terms of sensitivity? Well, one is these novel SPECT scanners that I mentioned right at the outset, where with Ring CZT systems, there's been reported to be able to reduce the scan time by 50% or more. Huge savings in scan time. Or we also have, the growing use of artificial intelligence techniques. And in this example, what they did was reduce the number of projections in the SPECT to try and reduce time. Of course, artificial intelligence can also be used to denoise images as well. And in dosimetry applications, I mentioned about having to do multiple time points. Well, there are ways by using either population time activity curves or looking at the time activity curve in the first fraction of these radioligand therapies to predict the dosimetry in future cycles by just using a single time point. And of course, that will help us massively reduce the burden to the patient and also to the clinic. Something else we should be aware of is the choice of iterations and subsets we use in our SPECT reconstruction. The more iterations and subsets we do, the closer we get to the true image and the true quantitative values. But more iterations and subsets makes the data noisier. And the speed at which we get to this true answer, the speed of convergence, is different across the image, which makes life challenging. Just want to show an example here. So this is one of my phantom images again. So this is the number of updates, which is the product of the iterations and subsets. And you can see quite clearly, while in the early number of updates, we don't really see good contrast between the features. It gets better and better as we go through more and more updates. But equally, we can also see that the image here at 100 updates is really quite noisy, particularly when we compare to what we had at 10 updates. So, the idea is to get convergence, but it does increase noise. And so we've got to deal with that noise, and the solutions are to think of smoothing, although there's consequences of that, in that we could reduce the actual uptake we measure by applying smoothing, or we could use reconstruction that's now available with priors, such as Q-Clear from General Electric. Motion is another issue, but here our solutions are limited somewhat. So we know we have involuntary motion. That could be cardiac, where we actually do have a solution, and that we can use ECG gating to try and correct or to handle cardiac motion. In fact, we do so quite regularly when we do a myocardial perfusion scanning, for example. With respiratory motion, I'm not aware of any gating being available for SPECT yet. Of course, it is available in PET, but in SPECT, where we're taking projections as we're moving around the patient and as the patient's breathing, it can be a little bit more complex. But maybe it doesn't really matter about respiratory gating, given the SPECT resolution we have. If we have a SPECT resolution of 1 centimetre, does respiratory motion really degrade what we can see that much? I'm not sure. Then, of course, we have voluntary motion. We know our scans can be long and patients can move. And what makes life a bit more complicated to PET is that in SPECT, motion can happen between projections. So we have, some discontinuity. We have some challenges with the projections then, where the patient may be in a different position in one projection compared to another. We know that there is currently commercial motion correction software available, mostly for cardiac applications, sometimes for brain applications as well. But in my experience, the success of this software is really quite limited. Finally, a limitation of quantitative SPECT is that there is no SPECT DICOM standard for quantitative SPECT. Also, there's some kind of divergence where if you have a SPECT brain, for example, you get one file, one image file, where if you did a PET brain, you would have a file for every slice. Said the quantitative SPECT has no DICOM standard, and manufacturers have their own way of handling things. There's a lack of transparency. And then if you have your quantitative SPECT data, it might work quite well on your manufacturer's viewing station, but as soon as you transfer to PACS, things don't work. Fortunately, people are trying to engage with the DICOM committee on this. There's a new group being formed by E&M, EFOMP and SNMI to engage with the Nuclear Medicine DICOM committee. So I've highlighted a lot of challenges that we face in quantitative SPECT, and harmonization, I think, can help a little way. With all the variability coming from acquisition and reconstruction, how do we know that the SUVI measure is the same as what you're measuring? How do we know that the kidney dose that I measure is the same as what you're measuring? And in SPECT as well, we now have harmonization on the agenda. So I'm working with the group with E&M Earl and ArtNet, and RSNA Kiba have previously done work in this area as well. So harmonization is coming, and hopefully we can get more consistent measurements from the scanners across our various centres. This concludes this presentation. Thank you for listening.